Have you seen the software? Other software? What are the things you learn over there? Like, things are shown, all the execution parameters. What all was shown there? Can you tell me?
EBST only they shown how to collect the data. They said the analysis will be done.
Right. Okay. So once you open the software, this is the Apex. Let me the PHP software as a medium. So I can create a new project. Let's say for test or training. That's the sample number 1. It will ask to save it somewhere. So I will save this raw file format. And basically in this software you have two modes. One is your EDS mode.
Okay, sir.
So EDS was also explained to you, like how the data acquisition is happening. Then you can go for this EBSD tab. So where it will show you the EBSD options. So yeah. So as did he tell you what are the SEM conditions or what are the SEM parameter needs to be there for the EBSD part? What are the
So they
parameters you
said the
want?
CI value should be in between 0.5 to 0.9.
That is for the EBSD part.
Yeah.
But what should be the SEM parameters before doing any
The
EBSD scans?
So the
20 voltage.
so the working distance should be between 8 to 10 mm, and the EHT should be 20 kilo.
Yeah, typically we do that. And what about the beam current? How much the beam
Sir,
current?
sir, 120.
Yeah.
Sir, battery part then it is 20 kilovolt maybe.
Most of the yeah, it is 20 kV.
Then it's 5 kilovolt or 5 to 10 kilovolt.
Yeah, that is true for EDS.
Yeah.
But for EBSD, typically you need the higher kV, that's in the range of 15 to 20 kV. But most of the time it will be typically 20 kV. Otherwise, at 5 kV it will be difficult to generate this kind of diffraction pattern. And we will see. So your sample has to be at 70-degree tilt. Your sample for EBSD will be. You guys are familiar with EBSD, all of you?
Yes, sir.
How many of you have used EBSD before?
So just analysis part I have done.
Okay, you've
Nothing
done
more.
it before. Anybody else?
No,
who's
sir.
done EBSD before?
No, sir.
Or are familiar with EBSD? No. So you were part. So you were there in the lecture, Professor Nilesh Gaurav lecture. You were there, no?
Yes, sir.
So basically, you need three things. One is sample should be 70-degree tilted, because at that condition you will be able to get more of your backscatter electrons coming out of your sample surface and reaching to the phosphor screen. Then the SEM parameter has to be around 20 kV. Probe current or beam current you need larger than regular SEM imaging. So in case of larger SEM imaging, you might go for lower aperture size, around 30 micron or so. But for this EBSD, typically you want more beam current to generate these kind of patterns. Typically you will go to 60 micron or 120 micron, and there is an option of high beam current option is there. So you can enable that option also to get more beam current out of your SEM system. So once you are okay with the SEM parameter, then you can collect the same SEM image into this EDAX software or Apex software. And once you are okay with all these parameters, then you can insert your EBSD camera. This is just a demo software in your laptop, so it won't be able to do anything related to hardware, but you can expand this option and you can insert the camera. So once it reaches up to a particular defined value where the calibration was done, it will reach up to those values here, and then the camera movement will stop. So once your camera is inserted, then the next thing will be to optimize the camera parameters. So has it shown you how to optimize the camera parameter? So basically couple of parameters are involved with this EBSD camera. You have predefined settings here. So depending upon your requirement, you can choose one of the settings. Let's say if you want to get the best pattern out of your EBSD sector, so probably you will choose this best pattern option, and then you can optimize the camera parameter. So right now if you see my binning is 5x5 binning, the gain values are almost 0, my exposure is basically around 11. And then now if I click on optimize, just try to observe those parameters, how the software changes those parameters, gain, binning and exposure values. So if I click on optimize, so based on the intensity of your diffraction pattern, it will optimize those parameters for you. So from binning of 5 by 5, it has gone to binning of 1 by 1. And also the exposure from 11, it has gone to 3 millisecond. So based on the diffraction pattern, it will change your camera parameters. So in this case, let me try to optimize it again. Let's say maybe point analysis. And then if I again click on optimize, it's a demo software, so it may not be configured for that particular point. So now you can start seeing the diffraction patterns. The moment I go to different region of my grains or my field of view, I can start generating these patterns from those particular points. So if I click here, my pattern will get changed. If it is part of the same grain, then the pattern will look similar, but let's say if I go to some other grain, let's say somewhere here. On the live system you must have seen this because it's a demo software, so it might not get changed. Typically it should change, but anyway, basically the point is the moment you go to different grain, the orientation will get changed and hence your diffraction pattern will be changed. So before applying anything on top of this, before doing any EVG measurement, you have to define your phases. So all these were shown to you, this phase definition and all.
Yes, sir. No, sir.
So basically what happens, now you have a database, library of database of particular phases. You need to assign that particular database to your actual diffraction pattern. So I know this sample is for the standard nickel sample. So I'll go to this phase tab, I'll search for nickel here from the database. I have a library of particular phases. I can directly type in nickel here. So whatever phases are there along with nickel, it will show you how much results, how much search results. Now these are the default phases which was there earlier for the earlier scans. So probably I can remove that and I can input this phase to this current phase list. So now basically what software will do. So now I'll close it. So now if you see the nickel phase is enabled here. So basically what software will do, it will try to match against this particular database. So let's say if I click here. So if you see in the background, the gray scale pattern you are seeing, diffraction pattern, that is coming from your sample surface. That is basically the raw pattern. And whatever this color coding you are seeing, that is basically your coming from database. So now it is trying to match the diffraction pattern against that particular database based on the library which was created. To show you something on the left, but I have to change it. Anyway, we'll continue on this one. So the moment I go to different grain, in this particular case it's a demo software, so it's not changing here, but ideally your pattern will get changed and then it will match against that particular database. So in this case it is not happening somehow. So typically if it is matching perfectly, right now if you see some of the bands are not matching with the actual database. So if you see this pattern, this band here, it is not getting indexed here, this pattern is not matching, this pattern is not matching, so it is slightly off your actual pattern. So maybe some calibration issues there, or maybe we have loaded wrong file here, this database does not belong to nickel maybe, the sample might be different and the database which you have loaded, that might be different. So that is another reason which is not able to index it. But let's assume everything is fine, it is able to index it, then my CI values will be higher. Right now the CI value is 0. That means it's not able to match this database along with your patterns. So if CI value is above 0.1, that means we can consider that your reliable data is there. Like confidence index, as the name suggests, this is how confident your software is in order to identify this as a reliable or accurate result. So in case this particular case it is 0, that means the data matching is not happening properly. If it is above 0.1, that means the data matching or the indexing is perfectly working fine. So let's assume everything was done here, and now after that you will get output from EBSD map. I'll show you in the analysis software. Maybe I'll delete everything. I'll start it again. So this is the IDEX OI analysis software. So once you open, the user interface looks like this. And if you want to open any of the data set, you can simply open that particular file. So in this case, I will probably open one of the 12 phase material. Let's say 12 phase titanium file. So once you open the data set, it will read all those values, like what was your calibration values for the EBSD detector, what was your working distance. In this case, it was collected at 15 mm working distance. Then what was your sample tilt, how many number of points it acquired. It acquired total 14,501 points, and out of that almost everything except 1 point was good points. That means the CI was good for all these number of points. And also it will show you the what was the dimension during the scan, how much area you had scanned. So X was 20 micron and Y was 17.41 micron. So this much area was scanned during the EBSD scan, and along with the step size was 0.1 micron. So every 1.1 micron step the pattern was collected, and so on. The entire field of view was measured with EBSD. It also shows what was the average confidence index. As I mentioned earlier, if confidence index value is above 0.1, that means your data is almost reliable. In this case, as it was from some good database, the confidence index value was much higher. CI typically ranges from 0 to 1. So if it is in that range above 0.1, then it's a reliable data. And also it will show what are the phases they are scanned with. So titanium alpha and titanium beta. So now if I want to analyze this particular data, the first data which you will get from any EBSD software is this IPF map. We call it as inverse pole figure map. So here in this all data, either you can show the IPF map for all over the data, like all data which includes both alpha and beta phase. So if you see in this color coded map, so titanium alpha is basically your hexagonal structure, titanium beta is cubic. So both the phases were added during the measurement, and based on that it has identified titanium alpha grains as well as titanium beta grains. Now if you want to see those alpha and beta grains separately, then I can select this alpha phase and then I can click on inverse pole figure. So whatever color region you are seeing, that belongs to your alpha grain. The white region belongs to your beta grains. Similarly, if I want to see the grains only for the beta phase, I can again click my IPF map. Whatever colored image you are seeing, those are your beta grains basically, and white region belongs to your alpha grains. So either you can do all the analysis on all data, or individual phases can be selected, and then you can do the individual analysis on those data set. So let's say I am working on all data. Then the next image which I can generate is IQ, which is basically image quality map. So what it shows, it shows the image quality map of based on your intensity of diffraction patterns. So wherever you have more intensity of diffraction pattern, those areas will look brighter in your image, and at the grain boundary, of course, you are having very grain boundary, because you are not seeing any pattern, so it will look appear darker in your image quality map. So by that we also, all these twin boundaries are also dark, because these are the twin boundary within the grain. You are forming this twin boundary, and you can also see the grain boundary information, like what kind of grain boundaries are available in your microstructure. So these are the default map for different grain boundaries. So all the red ones are 1 to 5 degree, all the blue ones are, the green ones are 5 to 15 degree, and all these blue ones are 15 to 180 degree. So these are the predefined maps, but if you want, you can change these parameters. So let's say for some region, if you want to see only one kind of particular grain boundary, so I can edit that. Instead of 1 to 5, let's say if I want to see 1 to 15 degree, typically 1 to 15 degree we consider it as a low angle grain boundary. So I can select, let's say, one particular color for low angle gain boundaries. I can remove probably one of them. And let's say 15 to 180 degree, I'll keep it as high angle gain boundary. I can define another color to that. And then if I click OK, now it will show all the grain boundaries in that color coded map. So 1 to 15 degree here it shows in red, 15 to 180 degree it is showing in green. And also the length of those grain boundaries will be there, what are the fraction of those grain boundaries. Out of 100%, 36% grain boundaries are your lower angle grain boundaries, around 64% are your high angle grain boundaries. So again, the presence or absence of these grain boundaries also will affect your material properties. So many of the cases they will try to see what kind of grain boundaries are there in your material. If there is any particular special kind of boundaries, have you heard about CSL boundaries, twin boundaries? The presence of those boundaries also will affect your material property. So you can alter your microstructure to generate those kind of boundaries, and hence those kind of boundaries will affect your material property. Your material will behave differently in presence of those kind of grain boundaries. So you can do this kind of analysis also. You can get texture analysis also out of this.
Sir, once we have removed one grain boundary, how to add that one?
So there's a default template or default icon is there, grain boundary quick map. If I select my all data and click on this grain boundary quick map, it will again replot it based on the default data set.
Okay.
Again, if you want to modify it, just do a right click, go to properties, and you can double click on that and you can define your own parameter. You can choose the color of those grain boundaries. That way you can change.
Okay.
So this was about the grain boundary. Also you can have the phase map for both the faces, like what is the fraction of those faces. So this particular map will show you the phase quick map. So now you are seeing the phase map for all the data. So whatever red grains you are seeing, those belong to alpha grains. Whatever greens you are seeing, those are the beta grains. So the alpha grains is almost 74% versus beta grain is 26%. So you can also get the volume fraction of your phases present in your material with this kind of phase maps. So this is also one of the important tools. Again, you can have the grain size measurement. Like what is the grain size of your sample? So it is area fraction versus grain size in diameter. Then if you want to show your texture results, then you can also plot in terms of discrete pole figure. So this is for showing a discrete pole figure, how your grains are oriented within this pole figure. You can plot the inverse pole figure also. So this is your inverse pole figure map, or inverse pole figure or the discrete inverse pole figure. So all these things can be plotted depending upon your requirement. You need to know what you are looking for this EBSD. What are you expecting? Like what is your interest of analysis? Are you interested only in grain size? Are you interested only in texture part? Are you interested in grain boundary? Are you interested in Taylor factor? Other features are also available. So are you interested on those features, or you want to create your own analysis? So suppose by default this is one of the IPF map is there. If you want to superimpose this IPF map over top of some other map, that is also possible. So for that you just need to do the right click, go to properties. Then let's say I want to see the combination of image quality and IPF map. So let's say grayscale image quality, and top of that I want to see the inverse pole figure map. That map is also possible. Now it will look slightly different. You can get some feel of, let's say, topography also effect will be visible in this image quality plus IPF combination.
So we can separate the IPF map also in different phases.
Different phases also, let's say. So this all data IPF map is, this is basically your IPF map for all the data.
Yeah.
If I generate the phase map, then it will tell me how the phases are distributed.
Yeah.
So this is basically, it will separate those phases in your IPF map. So like you can do multiple things. Even if you can create a map out of this, if you want to create a chart out of it, that is also possible. So different kinds of charts are also possible. If you do a right click on new, all these options will get enabled. So either you can create map, even you can create discrete chart. Let's say normal chart if you want to plot. I have multiple options here. So let's say simply I want to prepare, let's say a grain size diameter versus grain size ESTM number versus grain size intercept length. So depending upon type of selection you have chosen, it will generate those charts. And also this data can be exported in terms of raw data. So if you want to plot it in some other software, let's say
like
OG Excel,
origin.
that you can do a right click and then you can export a text. So let's let's say if I save next one. So whatever pretty pictures you are seeing, they are not just the pretty pictures, all the raw data is also associated with that is available. So where was file 1? So this is the raw data which you can get out of your grain size chart, and then you can plot it in OJ and Excel depending upon your requirement. You can use this data. And also few more important, some new features have come up with this software. So have you heard about NPAR? चाय ब्रेक लेना है? ठीक है, वो चाय लेते हैं, मुझे भी ब्रेक की जरूरत है. Software, one of them is NPAR. NPAR is basically neighbor pattern averaging reindexing. For that I will load file. I'll open one of the files from this high gain nuclear sample. So basically the .osc file will be the output of your EBSG scan. So whatever .osc file is there, this you will get from the EBSG sample or from the sample. So let's just open this. So again it will show all the parameters like what was the working condition, what was sample till, what was the, by mistake it shows 75. Might have captured 75, I'm not sure about that. But here all the dimensions, confidence index value. If right now if you see, the confidence index average value shows at 0.03. It is quite less. Typically we want it to be above 0.1. So now let's see what is the IPF map looks like. It should not be a great looking IPF map because my CI was not that good. So you can see all noisy data is there. If I can go to this flexi view, I can add my EBSG pattern flyby. Now if I take my mouse to different grains, now you can see the corresponding patterns on the right side. If you see the patterns are hardly visible. Those patterns are quite weak patterns, but still you have got some data out of it. Now let's see how to improve this particular data set. For that we have a thing called NPAR. I'll quickly show you what is NPAR means. NPAR is basically an offline technique where we are storing the pattern. During the measurement, we store all the raw patterns, and based on those raw patterns, we will do the averaging of those diffraction patterns. So suppose there is a 1 pixel, center one is 1 pixel of diffraction pattern. Now what we'll do, we'll take the average from nearby surrounding 6 neighbors, and those average value will be assigned to the center point. So by doing that, so we are improving our diffraction pattern quality. And once the diffraction pattern quality is improved, then with half indexing it is possible to reindex that. So same thing we will do here. So let's say this was my original data. Now I'll go to this NPAR option. For that, let's say go to image processing tab, and now my NPAR option is enabled here. I can do my background correction. So you see this was my original pattern. I take this value. Now I can apply my dynamic background on top of this, and I can do auto contrast brightness also here in order to improve my pattern quality. Though it might not look good to your open eyes, but for the software it is good enough to capture those information. So now once I save this option, then I can reindex by this option. Now if you see the pattern quality is bit better, same data is being captured again as an offline process. But to run this NPAR, you need to save the patterns along with your upticks. So by default, the patterns will not save along with the EBSG data. You need to enable that particular option. Maybe you might have seen it in the downstairs software. There is an option to store the pattern as well along with the upticks. So once you store the pattern, then only you can run with this NPAR. So now if you see the pattern is there, like the beam is moving from X to Y in raster fashion, and from every point it is generating one unique diffraction pattern, which is matched against the database after doing the averaging of those diffraction pattern. And you can see corresponding crystal structure, how it is changing depending upon the diffraction pattern, how the crystals are rotating. It will also show the status. like how much time is required, how many points it is capturing. Right now it's capturing around 200 points per second. Total number of points are these many total number of points. An average CI value for particular row is around 0.5 to 0.6, which is good enough. So you don't have to repeat your sample. Let's say for some reason you might not have got a proper EVSG scan, but still if you are saving the patterns, then you can run it offline without putting your sample again in the microscope. So by that way you can save a lot of time. So basically this is purely an offline process and part. So once the scan is over, I'll show the difference between these two scans. Here it will show the remaining time, around 16 seconds are remaining. So okay, once the data is scanned again, it will rename it as rescan. Now if I open this data, if I enable this IPF map, and now if I keep it side by side, you can see the difference. So this was the original scan, and this is after NFAR. So you can extract all those information even when you have the noisy patterns. So this technique is quite useful and very powerful. But only thing is that you need to save the patterns along with the original data set. And let's say if you're saving the pattern, the file of your data, like size of your data file can go very large. Let's say if in normal scan, if you are measuring, let's say 1 GB of data is there, if you save along with the pattern, it might go up to 10 GB, 15 GB, 20 GB kind of thing, depending upon your step size and number of points you are collecting within that scan. So it can be very huge files. And so many things can be seen, like grain boundary and all I have shown it to you, right?
Yes.
Grain boundary I have shown. Then if you want to have a particular highlighting option is also there. So let's say if I draw a grain size, so it will calculate the grain size here. And for some reason, if I am interested only in the grain size of, let's say, 10 micron, I want to highlight the grain size which has a grain size of 10 micron. So what I can do, I can select by my mouse click up to 10 micron or so. The X is micron, and then Y is your area fraction. So now what it will do, it will highlight those points in my IPF map. So now with the whatever grains has around 10 micron or 1 to 10 micron of grain size will be highlighted here. Then I can do a right click and I can separate that partition. I can click on the highlighted to partition. That means whatever highlighting I have done, it will create a separate partition for that. So now you got this separate partition which will consist of grain size only up to 10 micron. So by that you can separate your different grain size and you can do different analysis. Let's say for some reason if you want to calculate the pole figure only for these grains, then I can create a partitions of this kind. Then I can draw my pole figure, inverse pole figure for particular grain size. So this is one of the examples. On different basis you can do different highlighting based on grain structure, based on confidence index, based on, let's say, misorientation profile. You can do different kinds of partition over there, and then you can analyze your sample. And one more option you have, if you want to generate few of the important OM analysis, then for that you just select your all data, let's say this particular data, and then this auto option is there. So by default it will plot some of the standard analysis for you. Let me take it out again. Let me open that Platinum phase. So again, this is the dual phase starting material. If I want to do some standard analysis, I can just quickly click on auto. Automatically it will do at least 7 to 8 analysis. I think it will do it for you. So it will perform all those measurements or rather all those analysis. So all the basic one it will perform for you. So like your auto IPF is there. So this is auto IPF. Auto grain size is already there, which is there in the background. So this was auto grain size, auto misorientation angle chart it will create, auto image quality along with the grain border information. Then you can generate this auto phase, auto grain maps, auto IQ again, auto IPF. So one of the most common analysis it will do for you by using this auto option.
Notation. So we can also zoom the area
You can have this magnifier glass,
and
so by
do
that
the
you
same
can,
analysis.
yeah, you can do zoom it up. What do you want to do after zooming up? Like
Cropping.
what's it?
If we want to do analysis of certain area, like
Cropping
not
and
all,
all.
yeah.
If you want to crop that out, so that
Yeah.
is also possible.
Yeah.
So for that, just do a right click. This crop option is there. So let's say if you want to crop out one particular grain of one particular region, in this case, let's say if I
I
crop.
want to see the subgrains and customized grains like.
Okay, for that there is one more option. So this is a cropping, like say for some reason if you want to highlight only one particular grain or crop one particular place, you can do that. So now this particular grain was cropped, so now you can do the analysis on this for this particular grain. What you were saying the misorientation also. I'll show you one of the example for that. So let's say let's look at maybe this particular grain.
Subgrains.
Yeah, so though it looks like a single grain, but if you see
Small.
carefully all the like small division. There will be some deviation in the color, so that means some rotation is happening within the grain. So for that this option is there, profile vector. So if I draw, let's say from this particular end to another end of this grain, then it will show me the option for point to point misorientation and point to origin misorientation. So click OK. So now see, at this particular point maybe somewhere here there is a huge misorientation, not that huge but about 5 degree misorientation was there within that grain. So that might be because of the sub-grain boundary, maybe some twinning is happening over there. That twinning also it will show you here. So it will show you point to point misorientation as well as point to origin misorientation. Especially at the grain boundary, if you see there is a sudden jump over there. So let's say if I go from this grain to this grain, at the grain boundary there will be sudden misorientation will be there. So these are two jumps, one at this grain boundary and another one is at this grain boundary. So there is a high misorientation between these two grains because of this boundary. You have high misorientation. Typically around it is around 45 degree misorientation is there between these two grains. So all this information you can get. Then you can crop a particular grain. Let's say if you want to crop one particular grain, not cropping, highlighting one particular grain. With this, I think I can use this option. I can click on one particular grain, and then again I can do this endpoint to highlight it to partition. And one particular grain will be cropped out, and then you can do further analysis on this. Well, with so many options are available, like just IPF map is there. I can superimpose different maps on top of each other. So let's say in all data I have this IPF map. I can superimpose the IPF map over my image quality map as well. So let's say this is my IPF map. I can go to right click properties. I can select the image quality map as a grayscale map, and then it will be superimposed over my image quality map. All the different combination of maps also you can plot depending upon your requirement. Yeah, apart from so many things can be done on whatever data is available in form of the picture. It is available numerically also, so you can extract those data anytime.
GOS value we also can grain orientation
Grain
speed.
orientation spread, that also can be possible. First I'll show you CAM map basically. Kernel average misorientation. Again it's a kind of misorientation map.
Yeah.
So again there is a shortcut for that, CAM quick map. So basically it will show you the misorientation profile, misorientation map. Basically this is how we will close all this before. If you want anything, just do a right click and remove out of this project sheet. So this will basically give you the kernel average misorientation map. So here it ranges from blue to red. Blue is having lowest misorientation, red is having highest misorientation. So in this case almost it is blue and red, blue and green. So it's not highly misorientated. Mostly the grain boundaries you will see this misorientation profile. Similarly, you can do right click anywhere, go to properties. Instead of kernel average misorientation, I can plot Gauss, which you're saying, grain orientation spread. So all these options are available here in this right click. So grain orientation spread. Again, this is my grain orientation spread, which ranges from blue to red. So blue means lowest and red means highest. So there's a different kind of GAM, CAM, Gauss, all those things you can calculate. GAM will take longer time for calculation because it's very localized one. Anything specific you want to see here?
Sir, strain also.
Strain also somewhat you can represent in terms of this misorientation map, the CAM and all.
Yes.
That will give you some kind of misorientation data which basically you can correlate with the strain.
Yes.
And more or less you can export this data. Let's say the grain orientation spread data is there. You can export this data into some other software as well. So you can export the data, let's say cross correlation option software is there. So there you can calculate strain also. Not directly from this EBG software, but from other software you can import the data from this OM software and then you can calculate strain directly from there. I can see how my crystal rotates. The moment I go to different grain, you can see how the crystal changes from this grain to this grain, from this grain to this grain.
So how we can see the texture is better and
Texturing basically you can represent in three terms. So there are three tools to represent your texture data. One is pole figure, one is inverse pole figure, and another one will be ODF, orientation distribution function. So if you do a right click on this data, I can calculate the texture from here. I can add pole figure, inverse pole figure or ODF. Let's say calculate pole figure. By default I will take this one. So it will do all the calculation mathematics behind it. Harmonic series expansion it will do up to L16 series. Then I can plot, let's say in this case I'll remove this. So 001, 111, 110 pole figure it will plot. So this is how my pole figure looks like for this particular sample. And also you can plot, these are the regular pole figure. You can have pole figure in forms of discrete meaning also, but this is the binning pole figure. What I can do, I can do a right click. Instead of pole figure, now I can plot the inverse pole figure as well. So these are the inverse pole figure for that particular design. And again, it will be intensity will be there on the right hand side. So in case of titanium, you can probably see the difference between alpha phase texture and beta phase texture. So probably let me open that particular example. 12 phase titanium. So let's say if I perform the texture measurement pole figure only for alpha phase, let's see what it looks like. Because alpha is basically the hexagonal phase. So this is the pole figure for So this is a pole figure for alpha phase, and let's see how the pole figure looks like for beta phase. more concentrated somewhere along 001 axis. In case of the hexagonal structure, it is more along this 00001. It is basically a basal plane. Are you guys familiar with this concept of pole figure, inverse pole figure, ODF? Apart from you guys, like who are using? Because again, these are the stereographic position, as Professor Nilesh was mentioning in his lecture. These are the stereographic position
Yes, sir.
which we use to represent your texture data. Let's say this blue one is a random orientation and the red one is the highest orientation. So if all the pole figure shows you the blue color, that means this has no preferred texture. All the grains are randomly oriented. But if this clustering is happening in one particular location, that means it is generating some kind of texture in that particular direction or that particular orientation. So all this information you can show in terms of pole figure, inverse pole figure and ODF, which is basically a orientation distribution function.
So it is similar to the bulk texture analysis also. This is different.
Bulk texture is bit different because as the name suggests, a bulk measurement. Here it's a micro texture. We call it micro texture. So you are going to a particular location and you are measuring the micro texture. Bulk information sometimes can be misleading because your beam diameter at bulk texture will be somewhere around maybe 1 mm, 2 mm.
Their
beam
measurement
diameter.
is different.
Sorry?
There we can write the result from that measurement only in bulk texture analysis, or we have to be serious at the time of the experiment also.
No, I did not get
Same
the question.
bulk texture analysis, we have to do different experiment or same.
Yeah, it's measured through XRD.
Sorry,
Basically,
okay.
XRD also you have this bulk texture ganometer is there. The sample will be rotated in 3 directions.
From
like
same
it is-
data of the BST, we can draw the bulk texture analysis.
No. Whatever texture data you are generating from EBSD, that is basically a micro texture.
Okay.
For bulk texture, you have to perform another experiment with XRD.
Exam-
With XRD. Same sample you can take it to XRD and then you can measure bulk texture. For that, you need to have a ganometer which is basically which you can adopt for this. Because normal XRD, the backbend geometry will support only theta to theta measurement. For this texture, bulk texture, you need to have texture ganometer basically. So your sample will be moved in all 360 degrees, 0 to 360 degrees, and side rotation also will be there. So for that, you need a dedicated XRD system to measure bulk texture. But again, you try to correlate both the results, bulk texture XRD as well as micro texture XRD, micro texture EBSD results. Both results you can try to correlate. But for that, needs to be done through XRD.
Okay.
Yeah, we are almost running out of time. I think 5 o'clock is there. Any specific questions you guys have? You want to see anything specific?
No, sir.
I think it's too much for one.